Hello everyone. The mass spectrometer equations are very similar to what we did with Thomson's experiment. The only thing is that you're not dealing with just the mass of an electron anymore. You're dealing with the mass of some ion in this case. But we set these up exactly the same way. This is why I'm only going to do two examples, is because you've already worked with these formulas in a different unit for a different topic. But now you're just applying this to mass spectrometers. So the first example, an ion with a single charge. So we know what the charge is now, 1.60 times 10 to the negative 19 coulombs, passes undeflected through magnetic field and electric field. So we have the magnetic field of 3.25 times 10 to the negative 2 Tesla, electric field of 2.87 times 10 to the 3 newtons per coulomb. The electric field is then turned off, and then we're deflected through an arc with a radius of 0.425 meters. We want to know mass. It's a two-part question. First of all, in the undeflected region, we have electric force equal to magnetic force. Electric force, again, off your data sheet or off your formula sheet, is EQ or QE. Magnetic force, QVB. Charges divide out, so it leaves us with electric field equal to velocity times magnetic field. Second formula talks about us being deflected through an arc, so this is F magnetic equal centripetal, QVB equal to mv squared over r. Again, in this one, velocities divide out, and it leaves you with, since we're looking for mass, leaves us with a mass equal to QBR divided by velocity. So there's formula 2. Here's formula 1. What we need, the one thing we're missing is velocity, so we can go and create one single equation using these. Equation 1 manipulated for velocity is going to be equal to electric field over magnetic field, and we can substitute equation 1 into equation 2, or do these separately if you want. I'm going to do one single substitution. Sub equation 1 into equation 2, make one single equation, and I'll do some algebra after my substitution. So it's QBR divided by V, which is electric field over magnetic field. Now remember, when you divide by a fraction, it means to multiply by the reciprocal. So it's actually QBR times B over electric field. So my final formula, and then I'll do my substitution on the next slide, is QB squared R over electric field. And the one thing you have to remember, a lot of times students get a little confused with these complex fractions. When you divide by a fraction, means to multiply by its reciprocal, which is what I did in that second last step, multiplied by the reciprocal of E over B, which is B over E. And cleaned up my algebra. I have charge, I have magnetic field, I have radius, I have electric field. In this case, because the magnetic field is constant in the velocity selector and the ion separator, I could just use the same B. If they were different, I would have to put in the two different values. So in the next slide, I'll rewrite my formula. M equals QB squared R over electric field. And let's put our numbers in. It was singly charged, 1.60 times 10 to the negative 19 coulombs. The magnetic field strength is 3.25 times 10 to the negative 2 squared. 3.25 times 10 to the negative 2 Tesla squared. The radius 0.425 meters. 0.425 meters. Divide by the electric field, 2.87 times 10 to the 3. 2.87 times 10 to the 3 newtons per coulomb. And if we punch this in, just be careful that you don't forget to square the magnetic field. And you should get an answer of 2.50 times 10 to the negative 26 kilograms to the right number of significant digits. If you want, you're having trouble with the algebra and the substitution, then do this in two parts. Use the velocity selector to find the velocity, then plug the velocity into the ion separator region to find the mass. You always use the velocity selector to find V, then plug V into the magnetic force, centripetal force formula to find mass or radius is usually the two things you're looking for most often.